Listen, if you lose your main propulsion at sea, well, you're slow. But if you lose your electrical power completely, a full-blown blackout, you lose absolutely everything. Today, we're diving into the ship's electrical grid in this explainer, and we're not just talking about it like it's some basic utility. We are looking at it for what it truly is, the absolute foundation of a vessel's survival.
I want you to engage your imagination for just a second here and picture this genuinely terrifying hypothetical. What actually happens when a ship goes totally dark at 2 a.m. in the middle of the Pacific Ocean? The nearest patch of land is 1,000 miles away. There's no tow truck coming, right? There's no spare parts store right around the corner. It is a total blackout. What happens to the vessel?
Well, the immediate cascading failures are pretty terrifying. Losing power out there isn't just some minor inconvenience where your lights flicker and the Wi-Fi drops. No, you instantly lose main propulsion. You lose the ability to steer the rudder. You lose your fire pumps. You lose all your navigation equipment. You are plunged into complete darkness and a total loss of control all at once. The electrical grid is the foundation everything else stands on. Without it, you're just adrift.
So, to keep these massive floating cities alive, there's this underlying battle between alternating current, or AC, and direct current, DC. But AC almost universally wins at sea. Why is that? Honestly, it just comes down to physics and economics. AC voltage can be super easily transformed up or down, which allows ships to use squirrel cage induction motors. These motors are the absolute workhorses of the sea for pumps and fans because they are incredibly simple, rugged, and need very little maintenance. Compared to building equivalent DC machines, AC systems are just way lighter and significantly cheaper for the sheer, massive scale that ships require.
Okay, so how do we actually generate this AC power safely? It is really cool to look at how alternators have evolved over time. Older, statically excited alternators actually derived their rotor field current from their own AC output, which was fed back through physical brushes and slip rings. But modern brushless alternators? They use a small pilot exciter mounted directly on the same shaft, and by eliminating those physical brushes entirely, you drastically reduce maintenance and completely remove the risk of sparks. And in a fuel-dense engine room, no sparks is a massive, absolutely crucial safety upgrade.
But generating power is one thing. Managing it requires a small but incredibly mighty device called the Automatic Voltage Regulator, or the AVR. Think about the crazy scale of shipboard equipment for a second. When a massive ballast pump kicks on, it draws a huge surge of current. Without the AVR, the ship's entire voltage would violently sag every time a big motor started, and it would dangerously surge every time one stopped. The AVR continuously senses the output voltage and automatically tweaks the excitation current in real time, holding that voltage perfectly steady no matter what heavy machinery is turning on or off. It's working constantly in the background.
Now, having just one generator running often isn't enough. When demand spikes, or say you're maneuvering into a tight port, you need way more power. And that brings us to what is arguably one of the most dangerous routine operations on the entire ship, paralleling generators. Let me be clear, connecting two massive power sources together onto the same bus bar is not like plugging a toaster into a wall outlet. It requires immense, absolute precision.
To safely connect or synchronize two generators, you literally have to match three things perfectly before closing the breaker. You need to match the voltage, the frequency, and the phase sequence. The absolute best way to visualize this is to picture two people trying to jump into a spinning jump rope together. The voltage, that's the height of the rope. The frequency is the speed of the swing, and the phase sequence is the exact timing of the jump itself. If all three of those things don't align perfectly at the exact instant you close that connection, someone gets hit. On a ship, that means a violent electrical and mechanical shock that can physically damage the generator, shear the engine shaft right off, and totally destroy the switchboard.
So how in the world do engineers do this safely? Well, there's a golden operational rule they follow. Close the breaker slightly fast exactly at the 12 o'clock position. See, when an engineer is watching the synchroscope, which is this dial that tells you if you are in phase, a slowly clockwise spinning needle means the incoming generator is running just a tiny bit faster than the running bus bar. And that is exactly what you want. Closing slightly fast ensures the incoming generator immediately takes up the load, rather than being forcefully dragged by the running system like a motor. And you have to slam that breaker closed at the exact instant the needle hits 12 o'clock. Close enough is simply not close enough here.
But what happens when things go wrong and the system is overwhelmed? Say a generator suddenly fails, or the load is just too high. The ship actually has to protect itself instantly.
And this introduces a concept of what I like to call ruthless triage.
The solution is this brilliantly ruthless automated system known as preferential tripping. When the grid gets overloaded, the system just starts automatically shedding non-essential electrical loads in a preset priority order. It does this specifically to protect the absolute essential services from being lost in a wider blackout. Think of it kind of like a super smart household breaker panel that automatically kills your air conditioning and your clothes dryer during a partial power outage, specifically so your refrigerator and your lights can stay on. It sacrifices the non-critical to protect the critical, instantly. And when you look at exactly what gets sacrificed, the priorities of a ship become crystal clear. Essential services, things like the steering gear, navigation lights, and fire pumps are fiercely protected because they literally keep the ship and the crew alive. To save them, the system will instantly kill power to the air conditioning, the galley power, and the accommodation loads. Look, if the ship's automated brain has to choose between keeping your cabin comfortably cool and keeping the rudder working so you don't crash into a reef, you are absolutely going to be sweating in the dark.
Another fascinating way the ship protects itself is right in the architecture of its distribution network. Back ashore, your house is almost certainly earthed. If a live wire touches the metal frame of your washing machine, it creates an earth fault, the breaker trips immediately, and boom, the power is cut so you don't get shocked. But at sea, ships heavily favor insulated neutral systems. Why? Because on an insulated system, a single earth fault will not break the power supply. It just sets off an alarm. That means if a wire shorts out down in the steering gear room, you don't instantly lose your ability to steer the whole ship. You get precious time to locate and fix the fault, while still maintaining physical control of the vessel.
But of course, despite all these brilliant automated protections and fail-safes, sometimes the absolute worst-case scenario does happen. The primary systems fail, the secondary systems fail, we've reached the absolute last resort, a total blackout.
When the main generators die and the spinning stops, the ship is suddenly relying entirely on its battery banks, and the clock starts ticking immediately. You have roughly 18 to 36 hours. That is the amount of time a modern ship's backup battery system is sized to run. Now, obviously, this battery bank is not going to turn the massive propeller, but it is sized specifically to power your critical alarms, emergency lighting, and vital communications. It keeps the absolute bare minimum alive while the engineers scramble down in the dark to try and restart and resynchronize those main generators. And while those batteries are holding the line, your independent mechanical lifeline springs into action, the emergency generator. This machine is basically designed to be a completely autonomous survivor. It starts automatically the second the main power fails. It's located completely outside the machinery space, usually way high up on a weather deck, so if the main engine room is completely flooded or on fire, this generator survives. It even has its own dedicated fuel supply of light diesel oil for fast, easy starting. And it provides just enough power for the absolute essentials: steering, fire pumps, and navigation. It buys you the critical time you need to literally save the vessel.
Which really leaves us with this final, kind of provocative thought. We so often marvel at the sheer massive size of a ship's main engines, right? Those prime movers generate the massive physical thrust that pushes the ship through the water. But without this invisible, meticulously balanced electrical grid dictating every single valve, every pump, and every control loop, is a ship really anything more than just a giant floating piece of metal? I hope this explainer leaves you with a profound, newfound respect for the electrical heartbeat that keeps these massive vessels alive and fighting at sea.